Hey everyone, we're almost ready to begin our 2023 AMC 10B Livesolve. This one's going to be exciting, considering my performance on the 10A. There will be a little pressure to keep up the performance for this exam. I got a new sheet of scratch paper, and I'm almost ready to begin. Let's just wait for some viewers to show up. Welcome everyone. About to start the live solve for this session. As always, we will just be doing, going through all the problems, seeing how fast and how well we can solve the problems, and at the end, you feel free to ask questions while I go through it. Feel free to discuss. I will not be looking at chat until I finish my run, check my answers, and then I'll answer any questions that occurred during or after the live solve. So now's your chance to, maybe understand a little more about what I'm thinking when I'm doing these problems and some other things like that if you are curious. Looks like there are more viewers now. I'm really glad to see that people are trickling in. And we'll get ready to start very soon. I need to adjust some settings real quick. Sorry about this. Here's here, and then here's here. Alright, yeah, so give me 1 second to adjust this stuff. Got this kind of... Alright. Don't worry about this. Should be back to normal soon. Oop, okay. So here we go. Welcome everybody. We're almost ready to get started with the current run. Alright. Let's take a look how this goes. I'm just gonna do a little test and then we'll get started. Alright. Should be all set up now. Let's try this. Here we go. This is a test. Looks pretty good. Alright. So let's just fit this to the size. Alright, nice. Let's get started. As always, let me know if there are any issues with anything, but assuming everything's okay, I'm going to get started with problem number 1. Let me start the time at 5:08 p.m. So I'll be done at 6:23. 6:23. Just remember that. Alright, number 1. Mrs. Jones is pouring orange juice into 4 identical glasses. Fills first 3 completely, but runs out of juice when the second is only 1/3 full. So how much must Miss Jones pour, finish the first 3 so that all 4 glasses will have the same amount of juice? Well, if everyone has the same amount of juice, it's like 10/3 glasses. So 5/6 of a glass each, so just 1/6 of a glass from each of these. Just checking, right? Each person will now have 5/6 of a glass full. So that will give us C. Number 2. running shoes are on sale. Prices reduced by 20% on every pair of shoes. But he had to pay 7.5% sales tax. What is the original price of the most expensive shoes he could afford to buy? So like this. And then reduced by 20 is like this. Right, so this is like, if we just think about terms of like dividing by 2.5 or something like that, 40 on the top, like 43. Okay, and then this is like 4/5, and this is equal to $43. Cancels, $50, right? Are you sure? Yeah, so like 40 and then $3. So that should be B. Not sure why the answer choices are not in order this time, but yeah, that's kind of weird. Anyways, number 3, a 3, 4, 5 triangle is inscribed in circle A, and a 5, 12, 13 triangle is inscribed in circle B. Alright, so inscribed in means, of course, inside, making sure we are reading it correctly and not the circles inscribed inside triangles, but the other way around. So this one's the area of A to B, that's just going to be 5/13 squared. D, 25 over 169. Areas, just making sure. I always get area and perimeter mixed up, or I don't pay attention. So that's not, just make sure that you are answering the correct question, as I always say. Narrow strip of width this, 25 meters long, 6.5 millimeters. Just so we don't get confused, right? Just converting these all to centimeters, 2,500 centimeters, right? So our answer is just 2,500 times 0.65. That's going to equal 25 times 65, or 1625. The answer is C. See a list of numbers written on a blackboard. Adds 3 to each number. Okay. So like, and then multiplying each number in the list by 3 and finding that the sum of her numbers is also 45 means that the original sum was 15, right? So original sum was 15 distributed out about some number, and adding 3 to each number increases the total by 30. So that means there were 10 total numbers written on the blackboard for an answer of A. I'm really not used to these answers not being in order. If this is how it was on the actual test, might have been a weird break of tradition. Anyway. Number 6. Let L1 equals 1, L2 equals 3, with the famous Fibonacci recursion. This is going to be the Lucas sequence. How many terms are even? Alright, so it's going to be 1, 3, 4, 7, right, 11, and so on. We can just consider this mod 2, just taking odd or even. And it's going to look like this, right? 1 plus 1 is 0, 1 plus 0 is 1, 0 plus 1 is 1. And then, how many out of 1 to 23 are even? Well, out of 1 through 3, that's 2. Right, and they're going to be 2022 is a multiple of 3, so 2/3 of those first 2022 numbers. And then L of 2023 is also even because L of 1 is even. Or sorry. There we go. So our answer is just 674. E, right? Basically 1/3, the floor of 1/3 of 2023, giving us 674. Number 7, of course, for geometry problems, you always want to have extra room. So, I'm gonna start a new page here. How many this square is rotated 20 degrees clockwise. Alright, I instantly see circles here. Right? It's always good to draw circles when there are angles involved, and like any regular polygon. If this is rotated 20 degrees, that means this is 20 degrees. And we're asking basically what this is. Well, we know that this inscribes this angle, right? We know this is a 20 degree, and this total is a 90 degree, so this is 70 degrees, right? And then this is just 1/2, 75 degrees or 35 degrees. I'm sure there was an easier way using, for example, actually, there's probably an easier way, but it's just a lot easier when we write this, and that gives us an answer B. Okay. What is the units digit of this plus this? I know each of these has a period of 4, as in like if you have something ending in 2, then you go like 2, then 4, then 8, then 6, then back to 2. So that this becomes just 2 cubed, and this becomes similarly 3 squared. That's 8, that's 9, that's going to end in 7. Moving on to number 9. The numbers 16 and 25 is a consecutive positive squares whose difference of 9. How many pairs of consecutive positive perfect squares have a difference of less than or equal to 20, 23? So I guess that starts with 1 squared plus, or 2 squared and 1 squared, right? And that's a difference of 3. That's a difference of 5, right? And we know that the difference of squares of adjacent or consecutive positive perfect squares is just their sum. So the very last one's going to be 1012 squared minus 1011 squared. You can see that there are a total of 1011 of these. So our answer is just B. Have a difference of less than or equal to, yeah. Okay, number 10. You're playing a game. A 2x1 rectangle covers 2 adjacent squares of a 3x3 grid, but you are not told which 2 squares. So battleship, basically, right? And your goal is to find at least one of the 2 squares covered. A turn consists of you guessing a square, after which you are told whether that square is covered by a hidden rectangle. What is the minimum number of turns to ensure that at least one of your guess squared is covered by the rectangle? Alright. So I think we can find a construction of basically, if you imagine 5 or 4 possible positions of our battleship, right, of our thing, we know that we have to guess at least once in each of these. In addition, we have to check this lone one, right? In other words, right, there's no way to prevent us from having to guess at least 5 times, right? Because imagine right here, right, no matter which of the 4 of 5 you guess, there's a actually, I think our answer is just 4, right? Because it's just, sorry, this 1x1 square doesn't actually matter. Notice that if you guess these 4, you're guaranteed to hit 1. And there's no way to actually prevent guessing 3 from missing, right? Because imagine we pick 3 of these 4, then the battleship could have been the 4th unmarked one, and we would have lost. So that's that. Right, and there's no way to, yeah, I think that's a sound argument. So our answer is just C. Suzanne went to the bank and withdrew $800. The teller gave her this amount using 20, 50, and $100 bills, at least one of each denomination. So for example, 100 would have given $700 left. 50 times 12 plus 20 times 10, right? 200, 600, oh sorry, that's too much. 5. 100 plus 600 is 700. And then we can add 5 and subtract 2, right? So 10. So subtracting 2 here, adding 5 here, same drill, right? 6. And then we could have increased this by 2. Sorry, I keep doing this wrong. So it's 400 plus 300, yep. That still adds up. 4, 25, 2, and 30, and that's where we have to stop, right? Because we can't have 0 $50 bills. So there you go. That guarantees that. And then we also know that, right, imagine we use 2 hundreds, then you have 600 left. So the first one's this. And notice it's just the same, but every 50 gets reduced by 2, which tells us that basically 10, 8, 6, 4, 2. And we can see that there are only 5 cases here. With 300s, there would be 4. 400s, there would be only 3. And we can keep going, right? So 5, 4, 3, 2, 1. And finally, if we use, I think, 500s, then we only have one possibility, right? That would be if we use 2 50s and 5 20s. And that's the absolute minimum we can make with that, right? Absolute minimum multiple of 100, that is, using at least one of each bill. So that tells us that, indeed, there would be just 5 plus 4 plus 3 plus 2 plus 1, or 15 different collections, or that's not an answer. Hold on. How many different collections of bills? So what is missing here? The answers are out of 45. Oh, sorry, does it start at 6? That's right, yeah, it starts at 6. But something still, oh yeah, sorry. We reach 1 at 600 here. So our total answer is just 21. I was looking for a triangular number, because it's just a sum of like 1 through something, but I kind of miscounted. Luckily, 15 wasn't an answer, so we just luck out, I guess. Let's move on to number 12. When the roots of this polynomial are removed from the real number line, what remains is a union of 11 disjoint open intervals. Okay, so just basically, right, if you have x is really small, x is really big, or something in between. So let's take a look here. So x minus 1 here, and so on. Okay? Give me 1 second. Okay. Alright. So if we have this, I'm going to just assume it's this x minus 1 to the 1 instead. But like, if x is really big, of course we have positive. You know that 10 is a 10 times root, which means that if you, right, it's always going to be positive. In fact, right, the only times it actually changes sign is when we hit a single or an odd power root, right? So 1, 3, 5, 7, 9, right? And we would have like, basically, after 9 is always positive, right? Between 7 and 9, it's going to be negative because the x minus 9 to the 9 will be negative. And here's positive, minus, plus, and then minus, right? That makes sense because if we have this, there would be 55 total factors, all of which are negative, so we should end up with minus here. So we can see that out of these intervals, which ones are good? Well, everything before 1, so including, right, so of course the roots are just 1 through 10. So we would have plus, plus, right, minus, minus, plus, plus, minus, minus, plus, plus, minus. So because of that, how many of these intervals is p of x positive? 1, 2, 3, 4, 5, 6. So our answer is C. I'm gonna get some more info about this possible typo later. Alright. What is the area of the region in the coordinate plane? This looks tricky. Defined by this. So whenever we see x and y wrapped in absolute values by themselves, we know that we can just treat each quadrant separately. So we assume x and y are positive, right? And let's take a look. So I guess there are a couple of cases, right? If x and y are both bigger than 1, then what does that look like? Right? And we can see that that would look like something like this. If for example x and y are both smaller than 1, then it looks like this region, and I believe it's just a square, right? Basically, in the first quadrant, it's like the sum of the distance from the point 1, 1, right? It's basically a taxi cab distance, right? And we can see that if the distance is at most 1, then this means that we have this basically set of all points within 1 of this point, which is this. And of course, there are going to be 3 others that look like it. And each one has basically a square diagonal of 2, right? Because it's 1 in each direction. So the area of this is 2. The area of this is 2. This is the area is 2, whatever, right? And I guess the side lengths are root 2. Anyway, the total sum would be 8. You can see that the answer would then be B. Moving on to number 14. How many ordered pairs of integers here satisfy this? M squared plus mn plus n squared equals m squared n squared. Alright, given the answer choices, I'm thinking the answer is probably not that much, right? And we know that 0, 0 is a pair, and we know that if n works, then negative n works. So we know the answer is odd, right? 0, 0 is the only one that doesn't pair. So we can already eliminate D, but that doesn't really help us. So we know these are integers. I'm going to use okay, this is actually kind of, I'm gonna just try factoring, right, using SFFT. So we can write this as this, and then once we write it like this, right, okay, and then we say divide. I don't know. I'm trying to get like a good idea of like how this expands. And of course this is this, right? This is assuming m and n are not equal to 0. Of course, if m equals 0, let's just solve that individually, right? Just to get that out of the way. Then n squared equals 0, so then n equals 0. So if either of them is 0, we know that the pair is just 0, 0. So now we'll just assume m and n are not equal to 0, so that this is true. Notice that if either of m or n is now equal to 1, then we know that negative 1 has to be the other one. So like 1, negative 1, and negative 1, 1. Just because 1 would force this to be 0, then this would, mn would have to equal negative 1. So that gives that. And if n is any bigger than 2, then this is, something greater than 1. And if they're both bigger than 2, or 2 or larger, then this is less than 2. And we can basically do a pretty good bound on this, right? So you know that, first of all, we found all solutions such that either m or n is 1, and therefore also negative 1, I think. And we can just double check that, right? 1 minus n plus n squared equals n squared. Yeah, n equals 1, right? So we can verify that everything beyond this works. And then I think if you have like two numbers that are at least 2, then the product would definitely be pretty big, right? This has to be pretty close to 1, whereas the left basically is at least 2.5 squared, or 1.5 squared, which is already bigger than 2. So therefore, we can conclude that there are only 3 solutions, detailed as, well, 0, 0, 1, negative 1, and negative 1, 1. Moving on to number 15. What is the least positive integer m such that this is a perfect square? This does feel annoying, but we can use this nice trick, right? Because adjacent perfect squares are pretty similar. For example, 16 factorial times 15 factorial is just 15 factorial squared times 16. So in fact, this whole thing is a perfect square. But we can use the same idea, right? 14 factorial times 13 factorial is just 13 factorial squared times 14. And then all the way to 4 factorial times 3 factorial equals 3 factorial squared times 4. And then finally, just 2 factorial is just 2, right? So you can see that it's some perfect squares, which is nice, multiplied by this, 2 times 4 times all the way to 16, which is just 2 to the 8 times 8 factorial. And 8 factorial, right, this is also a perfect square, so we just need to find m times 8 factorial as a perfect square. That just becomes 2 to the 7, 3 squared, 5 to the 1, 7 to the 1. So we would need a 2, a 5, and a 7 for a total of 70. Answer of C. Nice. Yeah, so you can also see that, you know, every prime appears twice up to basically everything past 7. Alright, let's start on number 16 now. Define an up no to be a positive integer of 2 or more digits where the digits are strictly increasing, moving from left to right. So for example, 2, 2, 3, 8, I guess, is an up no. Define a down no to be a positive integer of 2 or more digits where the digits are strictly decreasing, moving to, this is not an up no, 2, 3, 8 would be, a down no would be like 8 to 0, right? Alright, so what is the difference between the number of up no's and down no's? Well, the only right, if you reverse an up no, you get a down no. The only difference is that down no's can end with 0, right? In fact, we can actually say that, I think this is true, that there are exactly 2 times as many down no's as up no's, just because you can take all the up no's, reverse them, and have the option to add 0, right? So in fact, the difference should just equal the number of up no's, and that should just be, well, you can pick out of, right, all of the digits have to be positive, there's no starting with 0. So in fact, it's just, right, some subset of these numbers, right, so 2 to the 9, but remember that, first of all, it can't be empty, and it can't have just one number. Otherwise, it's free game. Any subset of these will produce one up no. For example, 2, 3, 8 would be this subset of 3 elements. So this gives us a total of 512 minus 10, or 502. And and the number of down no's, I guess, and we'll just do this. Notice that we can do the same thing, right? This is going to be 2 to the 10 minus 1 minus 10. Notice that we don't have to worry about 0 being first because there are at least 2 digits. So this should be 1013. So I guess the question is, what's the difference? I see. So there are also down no's that consist of 1 digit followed by a 0. So that actually adds 9 to our count. So it would in fact be the total number of up no's, but there are also 9 extras. So this difference should be equal to 511, right? And that is E, right? It would be 9 more than the number of up no's. So my argument was, again, D equals 2u plus 9, so that the difference is just u plus 9. Alright, 17. A rectangular box P has distinct edge lengths here. The sum of all 12 edge lengths, right, is 13. So we know that if we have A, B, and C, then they all appear 4 times. So A plus B plus C equals 13 over 4. The sum of the areas of all 6 faces of P is 11 over 2. That means that since each face appears twice, that the sum of this is 11 over 4. And the volume of P is 1/2, and that requires no alteration. What is the length of the longest interior diagonal connecting two vertices of P? Of course, that would be given by this formula, which we can write as this, right? This actually is independent of the volume, right? In fact, we can just solve, right? This is 169 over 16 minus 2 times this is 22 over 4. That becomes 88 over 16. 169 minus 88 is 81. So that just becomes 9/4 for an answer of D. Very classic problem. I assume that's it. Right, just the most basic polynomial type question that you can get. Suppose A, B, and C are positive integers such that A over 14 plus B over 15 equals C over 210. Let's just multiply that out. You know that 14 times 15 is just equal to 210, right? So 15A plus 14B equals C. Which of the following is necessarily true? If, right, A and B are both relatively prime with 14 and 15, then C is relatively prime with 210. I don't think that's true. Actually, that could be true. Let's see. So so basically what we're saying is if either A or B is relatively prime to their number, right? And we can see that, like for example, let's just list out possible solutions, right? C, negative C is necessary as solution, right? So for A and B, so then we know that the general form is just C plus 14K, negative C minus 15K, right? And for some integer K. So that means that if GCD of this with 14 is 1, then we know that GCD of C with 14 is 1, but we don't know necessarily that GCD of C with 210 is 1, right? For example, 3, negative 3, 3, oh, they're positive integers. How's that? I guess we have to pick up the large C and then have this, wait, when does this actually happens very rarely. Pretty sure we can just list out all possibilities where this happens. Or no. Wait, am I thinking this through? Like the solutions here, for example, yeah, so like C is some, I guess it's better to write this. And okay. Anyways, like for example, if C was like, I don't know, something sufficiently big. But like for example, 3, negative 3 does not satisfy this, and then we can probably extend this, right, for positive integers. In fact, we can always add like 30 to A. It's kind of hard to make this argument. But yeah, I assume the answer is not 1. Then if C is relatively prime to 210, then C 14 and C of 15 are both equal to 1, right? Relatively prime to both of these. So that means that this number is also relatively prime to 14, right? Because GCD of this with 14 is equal to, I think 2 and 3 both have to be true, right? Because basically, if GCD of C and 210 is 1, then that means that C plus 14k, right? GCD of that, which is A, with 14 must equal just GCD of A and C. Sorry, C and 14, and we know that that's 1. Similarly, if C is relatively prime to 15, then the GCD of B, which is negative C minus 15k, with 15 must equal GCD of C with 15, which is just 1. So GCD of C and 210 equals 1 if both are relatively prime, right? But does it go the other way? Like, does there... I mean, surely, right? Like 4, or let's just give me a random number, like 11, negative 1, and then C. Oh, this is actually kind of tough. Right, is this true? Because if this is true, I guess my question is, we know that if GCD of C with 210 is 1, then that must be true, but if those are both relatively prime, then is GCD of C and 210 equal to 1? So if this is this is true, right? Because if GCD of C plus 14k and 14 equals 1, then GC of, right, is 14 is 1. So we know that C must be relatively prime, so 3 is true. Relatively prime to 14 and 15, which makes it relatively prime to their product, just because that's their LCM, they're relatively prime. So that gives us 3 is true, and 2 is true. So, because, I mean, right, because 3 implies 2. So then our answer just must be E, right? Because I'll come back to this, I'll find a counterexample for A. Make sure to add a big star next to it. Moving on, because I don't want to spend too much time on any one problem. I might come back to it later. Sonia the frog chooses excuse me, a point uniformly at random within this square in the coordinate plane, and hops to that point, right? She then chooses a distance uniformly at random, and then hops here. What's the probability that this, right, from northeast, south, and west? Okay. Well, then, if Sonia is within the region that is within more than 1 from the center or from the edges of the square, which is just this 4x4 square in the middle, then she is guaranteed safe. So there's a probability of 0 of landing outside of the square. Here it would be 1/2, right, for each of these, and for these it will be 1/4. So we can see that there's an area of, well, each of the areas of these strips is 4. So there's a total area of 16 out of 36 total cases where it's 1/4. And, right, and if you happen to be the unlucky 4 squares out of 36 that are the corners, then you actually have a 1/2 chance of landing outside the square. And then, of course, the probability is 0, so we don't have to even think about it. So this will be 4 over 36, 2 over 36, 6 over 36. That just equals 1/6 for an answer of A. All right. Moving on to number 20. The hard ones, I hope. 4 congruent semicircles are drawn on the surface of, it's creating... this is a baseball, and wow. Okay, well, this isn't too bad, right? Because if you look at the 4 points that divide the semicircles, right, and draw that, they're just going to form a square on a great circle of the sphere. In other words, the largest possible square inscribed inside our sphere, and the the radius is 2. So if that's the case, then the diameter of each semicircle is 2 root 2, and then we know that, right, if this is 2 root 2, then this is root 2 pi, right? Half of the diameter, in other words, the radius times pi, which equals root 2 times pi, and then the total length would just then be 4 root 2 pi, right? Because there are 4 of them. That's just root 32 for an answer of A. Moving on to number 21. Each of 23 balls is placed into one of 3 bins. What is the closest to the probability that each of the bins will contain an odd number of balls? Okay. So this is basically just saying pick 3 numbers that add up to an odd number, right? What's the probability that they're all odd? Alright, well, it's kind of weird because you're given that they're well then, what are the possibilities? Right, you could have odd, 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 which is the desired case, even, even, odd, bad, odd, even, even, and even, odd, even, right? So that should give us pretty close to the answer 1/4, right? But is this good enough? As in, like, are the parities just like half and half? Right, like, let's think about this, right? Are these 4 cases balanced, right? Well, yeah, I mean, right, it's pretty close, right? How many produce 3 odd numbers? Well, you can imagine 3 numbers like this, where alpha, beta, and gamma, right, 3 variables, are just integers, in fact, non-negative integers, and they add up to 23. And we can see that this is equal to 20, then that means that's equivalent to this, 1010. And then that has, by stars and bars, 10, 12, choose 2. For each of the remaining cases, the total would be just 2 alpha, right? 2 beta, and then 2 gamma plus 1 or something like that. And that's going to give us a sum of, instead of that, 1011, which gives us 1013, choose 2. So in other words, the total is this. Yeah, which is like very sufficiently close to 1/4, right? And in fact, we can actually find this number very quickly because we also notice the total number of possibilities, which is just simply, well, they add up to 2023 and they're all positive, so that should give us 3 numbers, like 2022, choose 2. Either way, right, it's most definitely the closest to 1/4, right? That is basically not a question, right? In fact, it's just going to equal 1012 over 2021, which is, or sorry, over times 2, right? Yeah, so I think we can safely say that's pretty close to 1/4. Moving on to number 22. I did have to convince myself of that result, because it could be very tricky, right? Because these numbers could be pretty close, but there's just no competition here. How many distinct values of x satisfy this? Interesting. So this means that Okay, so how many satisfy this? Well, it's obviously not an infinite number, right? Because this is bounded by like x minus 1 squared and x plus 1 squared minus this stuff, which do in fact, right, do that. So then let's just say x equals, we know that since floor of x is an integer, this means that 3x equals some integer, right, this. In fact, this means that this, and we also know that we can just say x equals, right, and let's do the first case where x is 3 times some x is some integer, because right, 3x has to be an integer, so either x is an integer or x minus 1 is an integer from this, right? So, or sorry, 3x, we don't know this, sorry. let me, floor of x is 0, 1, 1, 3. We know that 3x is an integer, so let's say x equals 3a for the first case. I keep saying this wrong. X is an integer, right? If x is an integer, then if you just have this, well then that's just this, right? So x equals 1 or 2, right? For those cases, and indeed those work, right? Say x is like some a plus 1/3, where a is an integer, then floor of x is a, like this. That would be a squared minus 3a plus 1 equals 0. Well, that doesn't give any rational numbers, right? It's going to be like 3 plus minus root 5 over 2. So that's not good. So that doesn't give any additional solutions. And finally, x equals a plus 2/3, which gives us a squared minus 3a plus 2/3 plus 2 equals 0. A squared minus 3a equals 0. That does give solutions, right? A equals 0 and 3. So our 4 solutions are then, and let me just do that, 1, 2, 2/3, right? And 3 and 2/3. In other words, 11/3. Let's just check quickly. 2/3 does satisfy. 11/3 should satisfy also, right? 11/3 does become 3, yeah. So that our answer is just 4. And that's the maximum number, so we know that we're done, right? Other than infinite, which we already eliminated. 23. An arithmetic sequence of positive integers has some number of terms, n, which is at least 3, initial term here, and Carl wrote down all the terms correctly except for one term which is off by 1. The sum of the terms he wrote down was 222. Apparently, there's only one possibility for this, or, right, a plus d plus n is constant. But let's figure this out, right? So we know that the sum of the terms is then also off by 1. So the total sum is either 221 or 223, not 222. This is, well, I think this one is feasible, right? Because it's 17 times 13, whereas 223 is, I believe, prime. Let me just quickly check that. 3, 7, 11, 13. Yeah, so definitely prime. We can't have prime numbers as an arithmetic sequence, so, or at least with at least 3 terms, that's probably not the case, right? Because, yeah, if you have at least 3 terms, then it's always going to be composite. So, for sufficiently large numbers, right? And we just need one solution, so it's more likely that we're getting it here. Well, let's say there are 13 terms, and the average is 17, right? And that should just work. And we know that if the average is 13 and the total is 17, or there are 17 terms, that should also work, right? Either way, right? And we can see that it extends in basically by 8 in each direction, like this. So that's one possible solution. And the other one should look like this, right? -6, like this. In this case, A equals 11, D equals 1, N equals, sorry, there are a total of 20, can't really think right now, 13, right, so that gives us 25, which is not one of our answers, which is, D is greater than 1, that's it. So, if we, yeah, so the D has to be 2 then, right? So that gives us 15, right, all the way down to, I think, 5, and then up to, well, plus 12, right, 29. So you can see that A equals 5, D equals 2, and N equals still 17. Or sorry, 13. So then that gives us a total sum of 7 plus, that's 20, B. That's not 13, that's B, right? Okay. Total sum is 20. Alright, moving on. 24. What is the length of the boundary of the region in the xy plane consisting of these points? This does scare me. Well, I mean, right, this kind of just has to be, right, like, since, oh, I see, okay. So what can alright, well, I think it's a parallelogram from what I can tell. But basically it's just like, take all possible points of the form 2uv, which is just this 2x1 region, right? Oh, it's not, it's a hexagon, right? So we take this and we can shift it by -3w 4w, right? And so for example, if w equals 1, that would form the following rectangle, which is also 2x1. And it's just like that, right? So the total perimeter would be 5 plus 1 plus 2 plus 5 plus 1 plus 2. That would equal 16, or an answer of E. On to number 25. A regular pentagon with this area is printed on paper and cut out. Okay. All 5 vertices are folded to the center of the pentagon, creating a smaller... Okay, this is weird. So that cut would look something like this, then this, then this, then this, then this, and we can safely assume, since this says it does create a smaller pentagon, that it's a regular pentagon, right? And these corner flaps won't stick out or anything, right? And yeah, that should tell us. All right. So this length is 1/2 of the total length to the there. So we can do a little bit of equation writing here. So with this diagram, let's just say the original side length is S, right? Then what can we say? Well, in any regular pentagon, we have 2 relevant values. The distance here and the distance here, right? And we actually know the relationship between these, right? Let's say this is A and B. That B squared minus A squared is this length squared, which is just S over 2 squared. And we can see that if we look at this, right, B prime and sorry, this is B and this is like A prime. If you imagine A and B to be the big pentagon and A prime and B prime to be the corresponding parts of the smaller pentagon, then we know that A prime over B equals 1/2. And A prime can be written as square root of, let's just say this is S prime. Then we know that A prime equals square root of B squared minus S prime over 2 squared. Okay. That's B prime, sorry. So from this, we should be able to figure out anything else. This actually feels better if we okay. Let's think about this actually. I think we should write everything in terms of like this ratio should tell us everything. Maybe I'm not doing this perfectly, so let me think. Yeah, so I guess we can pull out a this does feel like we do have to at some point use the properties of a pentagon, but I really don't want to use that, right? Like A prime over right, so I guess we just say S, and I'll just do it better, I guess, this time. Say this is B, this is A, then we know that this is like KS, this is like KA. So then we know that for some K, right, we get that KA over this length, which is B, equals 1/2. So K equals 1/2. Is that right? Okay. So we do have to find the ratio here. And then our answer is just K over S. Sorry, K squared times 1 plus root 5. So what is, I see. So what is this ratio? B over A? Well, that's, we know that's related basically to cosine or sine, sorry, of 54 degrees, that is. So let's draw a 54-degree triangle and try to figure out those. I remember there was a nice trick for that, but it's been so long. I guess we can use 36 also. Let's try to remember how this works. So A and B look like that. Then cosine 36, something. Yeah, I mean, we can say like cosine of 4 times 36 degrees is negative. There was a nicer way though, involving like, if you imagine a 7236, it's well known that this is like 1 to phi because of this. And then if you, alright, so then we can say like sine of 18 degrees equals, and that's the same as cosine 72 degrees, is 1 over 2 times phi, right? And then if that's true, then cosine of 36 degrees, which is what we want, right? That's A over B. And that's just equal to, well, cosine 2 theta is this. So then cosine theta equals square root of 1 plus cosine 2 theta over 2. So then it's just square roots of 1 plus 1 over 2 phi over 2. And then we need k squared, so k would then just be equal to 1/2 over the cosine of 36 degrees. And then square that. Okay, times basically 2 phi, right? In other words, and that simplifies to what? Phi over 1 plus 1 over 2 phi? And we should be home free here. And this is just annoying too. Right, I think like that's just gonna be 1/2 times what? 2 phi plus 1 phi plus, and then phi plus 1 is phi squared. That becomes phi over 1/2 1 plus phi, but then that just becomes phi squared. So it's just 2 over phi. Right, and that looks right. And then 2 over phi is just, well, this is just root 5 minus 1. Annoying, but I hope that's right. Alright, so that definitely needs checking. And then we said we needed to check number 18. Number 18, I've already verified 2 and 3. I just need to check if there was a counterexample for number 1, and that shouldn't be too hard. Like, there has to be some combination of these that just works. Like, let's just say 1, no. It's annoying. Okay. Maybe there's no counterexample. This or both is like kind of suspicious though, right? Like, we should not expect this to be true. For example, we can construct one, for example, where C is a multiple of 3, hopefully. And then that's going to be relatively, we can make that relatively prime to 14. Right, for example, let's try this. C is like some, like, 150, and K equals like 12 probably would work. No, that's too big. Let's try 180, right? So that would give us like 12 comma, oh, that's not relatively prime. Ugh. Whatever. 183, okay? C equals 183. K equals 12. Let's see what that gives us. The ordered pair 183 minus 168 is, I think, 15, right? No, wait. Okay. Like at this point where I'm like, I have to check all my math because I'm not confident in my arithmetic anymore. 15, and then 15k minus c. Oh no, this is too big now. 15k would equal 180 here. You get the idea, right? So, is there really no counterexample? I feel like there has to be, right? So instead of 183, I just have to subtract some amount. That makes it work. Okay. K equals 12 gives us that C has to be between 168 and 180. It's like 177, but that wouldn't work because that would give us, actually that does work, right? 9 and something, and then we know that since C equals a multiple of 3, 177, this breaks our statement. So like 9, and then just to check, that would give us 177, 3, I think. So if 9 and 3, then 9 over 14 plus 3 over 15. This should not have taken so long. I just realized that if A and B are just multiples of 3, then it just works, right? Like 3 over 14 plus 3 over 15 also works. That's just going to equal whatever this is, right? And of course, this 87 is not relatively prime to 210. So 1 is not true, 2 is true, 3 is true, giving us an answer of E. Yeah, so check that. But now, since I don't really have anything else to check other than... Okay, let's just check. Let's start checking here. I want to do some problems before I return to 25. So if he has $50, or if they are $50, 7.5% is gonna equal 7.5% of a sales tax on $50 is something weird. But we know that 20% off is 40, and then 7.5% of 40 is 3. So that works. Okay. I agree. Number 4. 6.5 times 25, but we can make 100 times as many, but also 1/10 as many. So 10 times that, which should give us 1625, right? Okay. I agree with that. Let's move on to number 5. So if there are 10 numbers, then the original sum was 15. Those work. So there are 10 numbers written on the blackboard. Perfect. Number 6 is going to be odd, odd, even, odd, odd, even. So 3, 6, and so on, up to 2022. That would equal 674. Nice. Okay, number 7. If this is 20 degrees, yeah, I mean, I guess the easiest way is just think of it in circles. Right, this has to be 20 degrees, and this is 70 degrees, and this is half of 70 degrees. So that's just 35 degrees. Number 8, that would be a 9. That would be an 8. Okay, 2023 to 2022, yeah, that would be indeed adding up to 7. Number 9, it has to be positive, so 1 squared minus 0 squared wouldn't be counted. Everything else would work, right? So 10, 11, B. Here, I think my argument just works, right? Any 4 things, I can always find a battleship that is not covered by any of those 4 points. Other than, of course, these 4. Okay. So our answer here is 4. C. Number 11. Just double checking this top work here. So 6 numbers adding up to 21. Very nice. B. That looks right. Okay. Number 12. Okay, this was one I needed to check. So, like, of course, if it's really big, it's positive. If it's between 9 and 10, it's still positive. In fact, between like crossing 10 doesn't do anything, right? So, like, if you look at this, 10, 8, 6, 4, 2. Crossing 10 doesn't change the sign because x minus 10 to the 10 remains positive, at least not negative. But crossing 9 would change the sign. Crossing 8 wouldn't change the sign. Crossing 7 would. 6 doesn't. 5 does. 4 doesn't. 3 does. 2 doesn't. 1 does. And 1 is the last point at which we change, right? Notice that there are a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 possible signs here. And out of those, 6 are positive, 5 are negative. We get a total of C. Make sense? 13. If x and y are both positive, that tells us that x, y, distance from that to 1, some of those, so taxicab distance to 1, 1 is less than or equal to 1, that maps out a square that is entirely within the first quadrant. So then our answer is just 8. Okay? Nice. Moving on. Number 14. Oh, this is also one I need to check. After number 14, I'm just going to move on and check number 25. So in this case, I mean, I just agree with the logic, right? If you negate n or m, the left expression negates, the right expression is always positive if m and n are at least 2 in absolute value. So we can just check the positive cases. Right, for example, if m equals 2, 4 plus 2n plus n squared equals 4n squared, 3n squared minus 2n minus 4. And that just does not have integer solutions, right? Because 2 too big, 1 too small. Something like that, right? Yeah, so there do not exist other solutions. So it's just those three giving us C. Alright, let's move on to number 25. Just check that real quick. So does our value of A over B make sense? Well, let's check A over B squared. So that's going to be 1 plus 2, 1 over 2 phi over 2. Root 5 plus 3 over 8. What is that? About like 5/8? That's actually a little big. Am I sure? Like it should be about, I guess it should be about less than 3/4, right? Because if it was a 30-degree triangle, it would be 3/4. So I guess this number still makes sense. So then if that's the case, then we just need to, that's A over B squared multiplied by, 1/2 of the reciprocal. And then square that. So that's 1/4 of the reciprocal of this. That's going to equal 2 over 3 plus root 5. Root 5, 3 minus root 5 over 2. And then we need to divide this, or sorry, multiply. Where are we? So we're here. Multiply this by 1 plus root 5. So this giving us 3 minus 5, negative 2, minus root 5 plus 3 root 5 plus 2 root 5 over 2. That's just equal to root 5 minus 1. So we should verify that our answer is B. Indeed, that is less than our original area, so we can say it's B. 24 is fine. 23 looks fine. Length of the boundary, just making sure. Okay. Okay, at least 3 terms, n equals 13, average 17, initial term 5, total number of terms 13. That should all make sense. Yep. Okay, so that gives us a total of 20, B. Looks good. Moving on to number 22, just making sure all of these work. Yeah. No other restrictions on X. Good. Number 21 was this value. Pretty sure this was right. Just quickly thinking through this one also. Radius 2, these are diametrically opposite points, right? The baseball sort of thing. This is 2 root 2, that gives us the side length. No, sorry, the diameter is 4, giving 2 root 2 as the diameter of each of the semicircles. So root 2 times pi. 4 of those gives us an answer of A. Good. 19. Another way to think of it is like there's a 1/4 chance of being here, right? Basically, there's a 1/6 chance that you'll lose to a west, right? So this is just, yeah. So, right? So that's a region where you'll lose to west. So 1/6 times 1/4, and then multiply that by 4 for all the options. So our answer is just 1/6, right? In general, if it's a 0 by or n by n squared, we should expect the answer to be 1 over n, which is pretty cool. Outside, just making sure. Back to number 18, I guess. Okay, times I think run out 6:23, yeah. So I'm gonna think about number 18 real quick, and then we're done. Right. Because GCD A in 24 is true if and only if GCD of C in 14 is 1. And so therefore, right, if C is this, then they must be both true, and this is equivalent, because, right. Okay. Cool. So that's E. Okay. So that concludes the exam. So let's just hope we got number 16 right. I forgot to check that one. If I didn't have enough time. Let's take a look here. All right. Okay. Check the answer page. C, B, D, C, A, E, B, A, B, C, B. 12 is D. Sad. Alright, I'll check that. Number 13 is B. C. C. 16 is E. 17 is D. 18 is E. 19 is B. 20 is A. E. B. B. E. And B. So 2 wrong. I'm a bit confused. Let me check this real quick. That is not a good sign. I mean, it's a good score. I love this score. It's great, but oh. Apparently on the original test, some people had answer choices C and D flipped. The numerical answer should be 6, which was where is it? My numerical answer is correct, 6, right? So the answers were flipped here. So I would have gotten that one correct, I guess. Now the question is, what's happening with number 19? Let's think about this. Oh no, I totally forgot there was a distance part. Whoops, okay, that's fine. So picks a distance randomly in the interval here and a direction here. Let's just first pick a direction and a point, right? So if we look at this region only, let's say we pick north, then it's just gonna look like this, right? Let's say your distance from the top is D, and your value of the number from 0 to 1 is X. Then out of all possible, right, cases here, well, I think there's a half probability of crossing the edge, right? You can see that if D is very large, then X has to be at least as large. In other words, this. So there's always a half probability of losing. So the answer is actually B, right? Because I didn't take into account the extra 1/2 probability here, right? So essentially what I'm saying is it's symmetric based on north, east, south, or west. So let's just pick that first, north. Then we pick a point in the square. We know that if that point is more than 1 away from the top edge, we will never land outside the square. So then the relevant portion is this part where D, which represents the distance from the top edge, is between 0 and 1. In those cases, right, we get X is between 0 and 1. X has to be at least D to win. That's a 1/2. So the answer is actually 1/12 or B. So I guess a respectable 144. So everything else, yeah, everything else looks good. So for any of you who are still here, score was 144, pretty good. If you have any questions about any of these problems, we can quickly discuss these. I do have to get to dinner though, so make it fast. I think this is a relatively straightforward test. A lot of these typical examples of, like, for example, if you have the rectangular box, then you can write like basically Vieta's equations, or like these symmetric sums. That comes up very often, right? Basically, think of it in terms of polynomials, like this, right? This type of question where we have strictly increasing or decreasing sequences of digits is often also very commonly used on a test. Things like absolute value questions are very typical. This type of question has also appeared, for example, on the AME, probably on the AMC as well. And then I guess there's some pretty cool, like, they do a lot of, like, game theory questions now. But otherwise, yeah, this is a pretty typical test, right? There was nothing here that was, like, super bizarre. This was a pretty cool, number 22 was a pretty cool problem. Number 24 was a cool idea. I think it could be solved pretty quickly if you organize your thoughts, right? That is just some 2u comma v shifted by negative 3w 4w, which is of course just, right, some amount here. So you can imagine just moving a 2x1 rectangle up and to the left to this location by negative 3 and 4, and then seeing the area swept out, right? Or I guess the perimeter of the region swept out. So that's nice, right? And our answer is just E. If we have this, right, number 25 was a little annoying to think about, but once you find the ratios and figure out like what you need to calculate, it's not too bad, right? And also the hint of the area being 1 plus root 5 should give you the idea that, right, this has to be related to the golden ratio phi in some way, right, here. The thing I was referring to earlier when I was saying I don't know what the cosine of 36 degrees is, which everyone should know, right? It should be something, if you have the mental capacity, that you should know. Let's say this is, right, cosine theta, let's say theta is 36 degrees. Notice that 4 theta plus theta equals 180 degrees, right? In other words, 5 theta is 180 degrees. Well, then we can write, one thing we can say is cosine theta equals negative cosine 4 theta, and that's, well, we can write this, right? Since 4 theta is double 2 theta, we can write this, and then we can further, right, write cosine squared of 2 theta as, well, cosine of 2 theta is 2 cosine squared theta minus 1, that squared minus 1. So now we can just, right, given that this is going to be a quadratic in cosine squared theta, right? Or I guess it's not. It's going to be kind of weird. Doesn't seem like you can actually do anything with this. I was thinking that this would just work, but I'm not sure anymore. Right, something like that. But yeah, this doesn't seem to simplify nicely. I thought it would, right? But it just seems like a big quartic equation that, I guess you know that x equals 1 is a root, right? And that's basically it, right? That we actually 1 is not a root, is it? Yeah, it doesn't seem like 1 is a root. So I guess this is still like a little dead end. There are not that many thetas that satisfy this. I think actually negative 1 is a root. So x equals negative 1 is a root, and maybe we can find another number that such that this is true, right? And that would help us, right? In particular, maybe if theta works, then so does something else, right? Like these should come in pairs, right? So that's, I guess, the idea, right? 5 theta is like some multiple of 360 degrees plus 180 degrees. So it's like, well, it's basically you have 5 different solutions, and one of them is negative 1. Like in the plane, it kind of looks like this, right? Yeah. But in general, this is just a number you should just memorize by using the 72, 72, 36 triangle, right? We know that if we draw the angle bisector here, we actually get 2 isosceles triangles, right? This is a 36, 36, or not isosceles, but yeah. So this is 36, this is 36, so this is isosceles. And this 72 degree angle, this becomes 36, and this is another isosceles triangle. So actually, you have like really nice lengths here that we can work with, right? In particular, if you let this be 1 and let this be x, then this has to be 1 plus x. And you can see that the ratio would be 1 plus x, right, of this to this. By similarity, there are 2 36, 72, 72 triangles here. This is also, right, such a triangle. So it's just 1 over x, right? And you can actually solve for x here, because x squared plus x minus 1 equals 0. And you get like x equals something, right? It's like phi minus 1, where phi is the golden ratio. So therefore 1 plus x is just phi. So that then in order to calculate the rest, right, we can just do the rest. Right. All right. Any questions from anything else that you want to see? I think this is very, not necessarily boring, but a test where you kind of see where everything's going. Number 14 was a bit weird of a question, but like you can kind of see that for a large enough m or n, right, there's going to be no solutions, especially because m squared n squared just dominates this entire thing. The way I wrote it is kind of weird, but it did help me to figure out that if m and n are both bigger than 2, or 2 are bigger in absolute value, we just get, right, too large of an expression on the left and too small of an expression on the right. Right, and I guess that the inspiration for that was just I wanted to basically isolate m and n as much as possible, which would almost be there, right? But there was a little bit, there was that one which still kept that mn on the side. Luckily, this is a very small term, so we can still sort of do this analysis on like, are m and n big? If they're both big, what happens? And things like that. All right. Seeing as there are no more questions, I will end the live stream very soon. Your last chance to ask questions. Cool. Looks like we're ready to stop the stream then. Thanks everyone for coming. Again, score of 144. Pretty good for a live solve, though I would have wished for if I were reading questions better, probably a perfect score. Either way, I'll see you soon. Thank you.